Hi everyone. Today we're going to be learning what is an empirical formula and what is a molecular formula. These are going to be really critical for us in using lab data to try to figure out what compound it is that we are working with. So I'm going to show you the process and the steps that we take in order to calculate these formulas and how to try to make it as easy as possible. So some goals. We want to be able to identify what is an empirical formula versus what is a molecular formula. We want to be able to calculate it based on percent composition or from lab data. And we also want to be able to calculate a molecular formula, which we use the empirical formula to do. So what is an empirical formula? An empirical formula is the formula that shows the simplest whole number ratio of elements in a compound. So what that means is the formula can't be further reduced, okay? So let's say I'm looking at something like C6H12O6. That could not be an empirical formula because I can reduce the 6 and the 12 and the 6 to CH2O. That would be the empirical formula, okay? So when we're looking at formulas and trying to determine whether or not they're a molecular or an empirical formula, we shouldn't be able to reduce it any further if it's an empirical formula. So if we're looking at these examples here, if we look at our first one, H2O cannot be reduced any further. There's only one oxygen present there, so that is an empirical formula. If we look at the next one, N2O4, I could reduce that. I could reduce that to NO2, so that is not an empirical formula. If we look at C, which is the example that I just did on the previous slide, that is not an empirical formula because it can be reduced. If we look at the next formula in letter D, H2SO4, you cannot reduce that any further because there's only one sulfur there. So this is an empirical formula. And then if we look at P2O5, again, we can't reduce this any further. I can't divide either of these numbers and still get a whole number. So that's an empirical formula. So identifying them is kind of the easier part. The harder part is the steps to finding it. So I always like to start with this step-by-step process and follow this. So the first thing you do is you decide whether or not you're starting with percent composition or whether or not you're working with lab data. So let's say we're using our percent composition. We know how to calculate this where you find that it's 20% hydrogen, 10% oxygen, yada, yada, yada. If that is the case, if we are starting with percent composition, we are going to assume that we have 100 grams of that compound. So what that means, you can see that below here, what that means is if I find in my percent composition that something is 15% sulfur, I'm going to assume that it's 15 grams of sulfur. So I'm literally just changing the percent to grams. That's all I'm doing there, okay? Once I have that step completed, I'm going to take those grams from step 1 and I'm going to convert them to moles using the molar mass. Okay, so using what's on the periodic table and seeing what it is. So for example, if we were looking at sulfur, it would be 32.066 grams per mole, okay? Then I'm going to divide those answers from step 2 by the smallest of them. So let's say I have like a set of 3 different elements. Whatever one gets the smallest answer, all of them get divided by it. And then if needed, use a multiplier so your answers become whole numbers. So all of this seems a little weird to start with, but it will make more sense when we see it with an example. So keep in mind this step. If you want, I would maybe put a star on this slide because this is going to be really helpful for you as you go through and do these calculations. From step 4 here, if needed, use a multiplier so each answer is a whole number. So let's say we're starting with this first one. We have a compound whose composition is determined to be 88.9% copper and 11.1% oxygen. So what we're going to do is find the empirical formula and we're going to name it. So I know in this case, I'm only working with 2 elements. So my first step I'm going to be doing here, I'm starting with percent composition. That's what I've been given. And I want to convert those percents into grams. So what that means is, for the first step, I had 88.9% copper. I'm going to convert that to 88.9 grams of copper. I'm going to do the same thing with the oxygen. Convert that to 11.1 grams of oxygen. My second step then is converting those grams to moles. So 88.9 grams of copper. If I look on the periodic table, I know that there are 63.546 grams of copper in 1 mole. So I'm just using the atomic mass that's listed. That then is equal to 1.399 moles of copper. I'm going to do the same thing with the oxygen, 11.1 grams of oxygen. That molar mass is 16 grams in 1 mole. So I find that I have 0.694 moles of oxygen. So then step 3, we're going to be dividing these mole answers here, so what I just found, dividing them by the smaller of the 2, the smallest, which in this case is the oxygen. So I'm going to take the value I found here, divided by 0.694, and what that is equal to, in this case, is 2 for the copper and 1 for the oxygen. What that means, what I'm going to find, is that I have 2 coppers for every 1 oxygen. That's going to be the formula, in this case, the empirical formula. So I'm using, oh gosh, I thought that was a highlighter. Oh geez. I'm using those answers from step 3 to write my formula, okay? This particular element, when we put all these together, when we go to name it, this would be copper oxide. However, I don't want to write just copper oxide because copper is a transition metal. So I needed 2 coppers for every 1 oxygen. Oxygen has a -2 charge. So if I needed 2 coppers to balance out that -2, each one of them would need to be +1. So that means this is copper 1 oxide because it has a charge of +1. So let's try to do another example because practice makes permanent. Remember, cannot. So here we have an analysis of a compound composed of iron and oxygen, and it tells us it yields 174.8 grams of iron, 75.14 grams of oxygen. So in this step, we can skip step 1. So because we have these grams here, we have the iron grams and the oxygen grams, we don't have to worry about doing step 1 because step 1 is the percent to grams step where we're just changing the label from percent to grams. So in this case, I already have the grams. I don't need to worry about doing step 1. So what that means is I'm starting automatically on step 2. I'm going to be converting, oh, wrong thing. I'm going to be converting 174.86 grams of iron and 75.14 grams of oxygen into moles. So I'm going to look at the periodic table. I'm going to see how heavy iron is for 1 mole, and that is 55.847. I'm going to do the same thing for oxygen. 1 mole is 16 grams. So at the result of this step, I get that I have 3.131 moles of iron, and I have 4.969 moles of oxygen. So now these 2 values that I've just found are what I'm going to use for my division step. So that's step 3. So I'm looking at these answers and I'm choosing the lowest of them and dividing each by the lowest. So if I look here, my moles of iron are 3.131. That's the lowest answer compared to these 2. So I'm going to divide this by 3.131. I'm going to do the same thing, 0.131 down here. So I divide by the smallest. This is 1, and this is 1.5. Now, if you write a chemical formula that has iron, oxygen, 1.5, that doesn't exist. That's not a thing. So what I need to do is multiply 1.5 by something to turn it into a whole number. And what I can do is multiply it by 2 to turn it into a 3. Whatever I do to one element, I must do to another one. So it has to be equivalent. This is Fe2O3. And specifically, if we look at what kind of iron this is, oxygen has a -2 charge. There are 2 irons. So we know if the oxygens are -6, the 2 irons have to be +6. These are irons with a +3 charge. So this is iron 3 oxide. Okay, so that's how I would solve this. So just to recap, I skipped step 1 because I already had grams. I then converted grams of iron and grams of oxygen into moles of iron and moles of oxygen. I then divided by the smallest answer I got in step 2. My result was 1 and 1.5, and I used this multiplier to turn 1.5 into a whole number, resulting in my final answer. So let's try another one together because practice makes permanent. So now we are starting with percents, okay? So I'm going to change 10.81% into 10.81 grams of magnesium. Same thing with the chlorine, same thing with the oxygen. Okay, so what I'm going to do is convert these to moles. So 10.81 grams of magnesium. Turning that into moles, we know that there are 24.3 grams in 1 mole. This equals 0.445. Same thing for chlorine. Use that atomic mass. This awkward silence while I write everything. Okay, so now I'm finished step 2. I found my 3 molar values here. Boom, boom, and boom. So now I want to divide them all by the smallest. So if I look here between the magnesium, the chlorine, and the oxygen, magnesium is the smallest. So I'm going to divide this by 0.445, divide this by 0.445, divide this by 0.445. Answer here is 1, answer here is 2, and the answer here is 8. So I don't have to worry about doing that final step where I multiplied to get whole numbers. I got whole numbers. So I'm going to look here and see that I have Mg, there's just one of them, Cl2O8. But if I look, when I have Cl and O, this is not a polyatomic ion. So if I look on my polyatomic ion chart, ClO4 is a polyatomic ion, but Cl2O8 is not. So I want to change this into MgClO4 2. Okay? So how does this then vary from a molecular formula? So a molecular formula is showing the actual number of elements. So it could potentially be the same as an empirical formula, or it could be a multiple. So an example of this would be sugar. So glucose is C6H12O6. This is not an empirical formula. The empirical formula for sugar would be CH2O. But in nature, if I'm looking at a molecule of glucose, it doesn't have 1 carbon, 2 hydrogens, and an oxygen. It has 6 carbons, 12 hydrogens, and 6 oxygens. So they can be the same formula, but they don't necessarily have to be. Molecular formula is showing the actual number, what is really happening inside of that molecule. So in order to figure out what a molecular formula is, you're going to use the empirical formula and what its mass is. So specifically here, the mass of the formula. I'll put molar mass here. Oops, I don't want to put that. Let's just put mass. So the mass of the empirical formula. So to find molecular, I'm going to need to find this N value. So in order to find N, I'm going to take the molar mass, which is going to be given, divided by the empirical formula mass. So let's see what that looks like. If I have this particular problem, I have a compound that's 80% carbon and 20% hydrogen. So I'm going to go through and determine its empirical formula just like I did before. 80% carbon, 20% hydrogen. First step is to convert those to grams. 80 grams of carbon, 20 grams of hydrogen. Going to convert this into moles, so that's my second step. And I find that I have 6.66 moles of carbon, what a spooky number, and 20 moles of hydrogen. I'm going to divide by the smallest of these two, 6.66, 1, and 3. So my empirical formula is CH3. They're telling me in the next portion that the molar mass of this compound is 30 grams per mole. But if I look at CH3 and I add up the carbon and the 3 hydrogens, so if I'm looking here at this CH3, I know that carbon has a mass of 12.011. I know hydrogen has a mass of 1, but there are 3 of them, which equals 3. So this mass is 15 grams per mole. They're telling me the actual compound is 30 grams per mole, so that doesn't match. So what that means is I need to figure out what N is. And N is the molar mass divided by the empirical mass. So for this, 30 divided by 15 equals 2. So what that means is I need to multiply my empirical formula times 2. C2H6. Okay. Let's try another example. So here we have 92.3% carbon, 7.7% hydrogen. We're going to find the empirical formula first. So 92.3% carbon, 7.7% hydrogen. We're going to convert that into grams. 92.3 grams of carbon, 7.7 grams of hydrogen. Okay. I then want to change these into moles, so go from grams to moles. I know that there are 12.01 grams of carbon in 1 mole, and for hydrogen, 1 mole is it's just 1 gram, okay? So I find that I have 7.7 moles here and 7.7 moles here. So my next step would be dividing by the smallest of the two. These are both 7.7. So I'm going to divide both by 7.7, which equals 1. So that means I have 1 of each, C and H. Carbon plus hydrogen's molar mass is 13 grams per mole. They're telling me the molar mass is 78 grams per mole. So that's not the same thing. So that means my molecular formula is different than my empirical formula. So I'm going to have to figure out what I multiply it by. It takes 78, which is the molar mass, divided by 13, the empirical mass, and I get 6. That means I'm taking CH times 6, C6, H6. And that would be the molecular formula. So by this point, you should be able to tell the difference between the two, calculate an empirical formula, and then calculate a molecular formula using that N equals molar mass divided by empirical mass. If you have any questions, please let me know. This can be a little bit of a tricky concept, so I want to make sure that you understand how to do it as best as possible.